All right, good morning, happy Tuesday, happy last week before a break. Yay, we're all ready for more of a break, I think. Yes. This week we're doing two things, review and then take an exam. That's all, okay? So today I want to step through each chapter and give you kind of a list of things to focus on. Don't think that it's comprehensive. There's, of course, other things. I just want to hit the highlights and give you an overview of what's in each chapter. And then we're going to do example problems from each chapter as well. And hopefully by the end of the day, you feel like fully prepared. You don't even have to go home and study. Maybe that's wishful thinking. I don't know. But hopefully it'll give you a starting point. So this exam starts with what we call Chapter 5B and 6. We didn't quite get through everything in Chapter 5 before the previous exam, so it sort of picks up where we left off. And the first thing that we talked about was the last one of our special forces, which was the spring force, which just think of this as a continuation leading into that spring force. Naturally, it's going to be hard to do a lot of this stuff in Chapter 5 and 6 without the rest of Chapter 5, because gravitational forces and normal forces and all those other forces are going to come into play in other problems. So don't think you can just forget about all the other stuff in Chapter 5. Let's see, the spring force, just for reference here, is K times X, as long as we're just looking at the magnitude. And keep in mind, it's an opposition force. It opposes being stretched or compressed. And it's always trying to get back to where it was, trying to get back to its natural length. Once we added that last force, there were basically two types of problems, more advanced force problems, if you want to think about it that way. We had the multiple connected objects, and we will do one of those in just a minute. Multiple connected objects, and we also had problems with uniform circular motion. Or I should say we solved problems with uniform circular motion. We didn't have problems with it, right? It was good. You understood it completely, maybe. We're going to do two examples of that in a minute, just to make sure that we're all on the same page, okay? That was wrapping up Chapter 5 and 6. It's basically those three things. So let's do a couple of uniform circular motion problems. And I zoomed it and it didn't get bigger. There we go. Okay. In this particular case, we have a plane. It is flying directly at you. I don't know that there's any plane that actually looks like that on the front, but you get the idea. It's flying directly at you. Its wings are tilted and it's sort of coming around and in a circle like this. So it's a flat horizontal circle, and the wings stay tilted exactly like this at all times. The only thing that they tell you is that there's something that we don't know about called a lift force, which points in that particular direction. That's really all you need to know about the lift force, because we're going to find the magnitude of it in just a second. What I need you to tell me is a couple of different things. First of all, other forces acting on the plane. Anything? Probably gravity, I would agree with that. So gravitational force straight down. Of the other forces we know about, can you think of anything else that might be acting on the plane? There would be some friction from the air, some air resistance. We don't deal with that in here. We're going to ignore the air resistance. Anything else? I think that's about it. It's just those two forces. So, based on the direction I told you the plane was flying, which way is the C direction? Point to it. Where is the center of the circle it's making? It's right over that way, right? It's flying directly at you and turning around like this, going in a circle. So the center of its circular motion is over here somewhere. We don't know how far over there. And we could say that the positive C direction points that way. The C direction is what restricts your problem. The C direction always has to point to the center of the circle, which is going to force the Y direction to be perpendicular to that, okay? The Y direction is forced to be perpendicular to the C direction, so it's really the C direction that sort of sets up the whole problem. Once we have that, Well, we have a free body diagram. What are we going to do next? What happens next in a force problem? Yeah, let's add up all of the forces. So we're going to add up the forces in the y direction, and down here somewhere we'll add up the forces in the c direction. Add up the forces in the y and the c direction. So that lift force that they've given us, it's kind of in between. So I'm going to have to break it into components. So let's see, we'll put a component directly up and one directly left. This one is going to be L cosine 20, and the one at the top will be L sine 20. And now we can actually add up all of the forces. Are we doing okay so far? You remember how to handle all this? Feels like it's been a while, maybe. So let's see, in the y direction, I only have two. I've got one that points up, one that points down. So that's L cosine 20 minus FG equals MAY. But if it's traveling in a horizontal circle, is it moving at all up and down? No. So that's going to be zero acceleration in that direction. It's staying at the exact same vertical height. It's not moving up and down at all. So I can rewrite this as L cosine 20 minus mg equals 0. And look at that, the only thing that's unknown there is L. So mg over cosine 20 will give me the magnitude of the lift force, this unknown thing that's keeping the plane up in the air that I don't think we get to learn about this semester. You'll have to wait till another physics class, okay? So let's see, plugging those numbers in. They told us the plane was 400 kilograms. G is 9.8, divide by the cosine of 20, and you should get a lift force of some value that I have here somewhere. I've got 4171.6 newtons, okay? Please stop me and ask questions if you've got them. Yes?
Sorry.
No worries.
C direction. What's the easiest way to find?
Think about the object's motion. There's a circle there somewhere. Where is the center of that circle? So an imaginary circle that's being traced by the object, wherever the center of that circle is, point your C direction that way. Okay, so here I've got a plane that's just doing this.
So we know that C direction is that way because the plane is tilted.
It's tilted and sort of flying at us around like that. Okay, so I had to tell you that information about the diagram for you to be able to deduce where the center of the circle is. And let's just add over here, this is the center of the circular motion. Okay, anyone else? Notice we answered part A without even reading it. It said, find the magnitude of the lift force. Yay, we did that, okay? The other one is, what is the constant speed the plane must be flying? You might get the idea it's probably going to come from the equation in the other direction, because that's how these problems work. There's only one force in the C direction, that's L sine 20. And remember that the centripetal acceleration is v squared over r. And now that we have a value for the lift force, the only unknown in that equation is v. So we can rearrange that and solve for v. So RL sine 20 divided by m, and take a square root, should give us v. So let's see, R they said was 1.3 kilometers. I need to convert that into meters, so 1,300 meters. And L is 4171.6, sine 20, and divide by the mass, which was 400. You should get a velocity of around 68 meters per second. Okay? Not a big plane, not a fast plane. There's one example problem dealing with circular motion. Stop me if you have questions. Anybody? Anything? Nothing? In the back.
What's that first one? Is it 1300?
1300, yes. Which is the radius given up at the top. The radius of the circular motion. Anything else? Yeah.
V squared over R was AC.
AC is V squared over R. I'll put a little note over the side. There we go. Anyone else? Good. Questions? Thank you for asking questions. I appreciate questions. Yeah.
So for the first part, where we said that AY equals 0, it's because it doesn't move up and down, right?
Correct. All of its motion stays kind of at the same level. It never accelerates this way. Okay. Anyone else? Yeah.
I remember an example from a while ago with the car on the traveling in a circle on a slanted plane. How does kinetic friction factor into that again?
For the car on a slanted plane, kinetic friction doesn't factor into that one. It doesn't. There was a type of friction there we were ignoring, and we dealt with static friction because we didn't want it to slide sideways. Okay. Shall we do a second example? You're like, yes, circular motion, please. Yes.
Why, so in top one, it said L cosine 20 minus infinity. So why in the bottom one didn't say minus?
On the bottom one, why didn't we say which part?
So the bottom one,
Down here?
part B, yes.
Okay.
Why did I have say minus the x?
Why not minus this? Okay. So
Is that because original force someday?
in the horizontal direction, it's because there's only that one. It's the only thing that we have in the C direction. So it's the only thing that goes onto the left side of the equation. So we didn't subtract anything else from it. We didn't put anything else there simply because that's the only one. In the vertical direction, we had one that's pointing up and one that's pointing down.
So that's because FG is a friction. That's why they're.
FG is gravity, gravitational force. Okay, and it's vertical, not horizontal. Anyone else? Yes.
That AC formula, that's the acceleration that it's going.
That's the acceleration in the C direction.
Okay.
It's the thing that's making it turn. Looking around at all of you, waiting for those other questions to seep out. As soon as I do this, the question will come. It won't drag. Drag, please. Oh, see, I knew it. It worked. Yes.
So we're expecting one circular motion question on the exam?
I can't answer that. Could be one on there. Could be all circular motion questions, but probably not. I can't say more. Let's do one more for practice. A pilot. What's with all the planes? I don't know. This pilot's a little bit strange because he places a bathroom scale on his seat in the plane and sits in his seat on the bathroom scale. I hope pilots aren't doing that, but whatever. And he notices his weight looks normal when read off the scale before taking off. Then he swoops down in a vertical circular arc of radius 60 meters and looks at the scale again and sees that it reads twice his weight. Okay? So let's imagine what's happening here. Like the plane goes wee down like that. That's not really a circle, but you get the idea. And then right here at the bottom, when in that circle, that's when he looks and sees the scale weighs twice as much. So what type of force is this? What does a scale measure?
Gravitational force.
Does it?
Well, I mean, how much weight is like the how much weight gravity is exerting on I don't know how to explain it.
Sure.
But wouldn't the force that, like, the amount of pressure you'd be putting on the scale be impacting how the scale is reading weight?
Yes. How much pressure you're putting down on it. So what does it do?
What is what?
What does the scale do? What does it do to you? Stand on a scale,
It pushes
Sure, math.
pushes up, right? Otherwise, like the scale falls or something. That's no good. Hopefully, it like pushes up at the exact amount that you push down on it. What do we call that force that it pushes back with? Yeah. The scale is actually reading what we call either apparent weight or the normal force. So they told us the normal force. The normal force in this problem is equal to 2 times the weight, 2 times the gravitational force. Okay, that's the starting point of this problem. The scale is pushing back with twice the weight. It has to support him as he travels in this circle. So let's think about the forces that are acting on the pilot at this point. One of them is apparently the normal force. What's the other one? Gravity, yeah. And if you imagine just the pilot like separate from the plane and everything else, that's it. The scale is supporting him and gravity is trying to pull him down. Nothing else is acting on the pilot. So if we imagine this circle that the plane is traveling in, the C direction points up at that point. It's a vertical circular arc and the pilot is currently at the bottom of the circle. So if you imagine like this is a very terrible flattish sort of circle that I've drawn, but you get the idea, okay? The center of the circle is above him. Notice all my forces are up and down. There's nothing sideways. So I'm just going to use the C direction in this problem. There's no point in using X because it's not going to have anything in it. There's no point in using Y because C is already in the vertical direction. So that's going to take care of all those forces. So notice the normal force points in the positive direction and the gravitational force points in the negative direction. And that acceleration is always v squared over r. So Fn minus Fg equals v squared over r. I like how I look around at your papers, and a lot of you drew bad circles to match mine. Don't do that. Draw a better circle than me. Be better than me. You can do it. It's like all of you drew this U. It's not a circle. The U is not a circle, but you get the idea. So let's see. They gave us the normal force, which is 2 times the gravitational force. And we also know that there is a gravitational force there as well. And 2 FGs minus an FG is just 1 FG. And FG is always equal to mg. So now I've got this. And then all of a sudden, well, things just are kind of done. Because I can cancel out the m's, and v is going to be the square root of g times r. And those are numbers we have, I think. Let's see, g is 9.8, and r, it said it was 60 meters. So the plane this time, let's see, how fast is it going? Ooh, really slow, 24.2 meters per second.
Sorry, what happened to 2FG?
2FG had an FG get subtracted from it. So 2 minus 1 is just 1. Okay? So imagine what this plane's doing, right? It's like he goes down, like swooping down and then curving upward in this circle that has a radius of 60 meters per second, moving forward at 24.2 meters per second, makes the pilot feel twice as heavy. It's like You feel like the extra pressure down into the seat. You can imagine what might happen if he like tries to swoop in a sharper circle. It's going to cause more problems, more what we might call G-forces. That's what's happening here. You can think of this as he's pulling 2 G's, meaning he feels twice the acceleration due to gravity. Or if he's traveling faster at that point, also more problems. He's going to feel even heavier than what he already feels. So you can just imagine the stunt pilots that are doing stuff way more complicated than this at way higher velocities. They're going to feel way heavier than just twice their weight, which is why they have to go through all that training not to black out and all sorts of weird things. Okay? Any questions about either of these circular motion problems? Does everything up there make some sense? Yes?
Do we know that it's twice FG right at the bottom from the problem?
From the last line of the problem. Yeah. And for this, you would have to remember, or I would have to tell you that the scale is reading the normal force.
So, let's say if this was the opposite direction,
Mm-hmm.
it would be the opposite. It would be lighter.
If it was at the top of the circle, would feel lighter. Yeah. And we could calculate that if we wanted to. If we assume maybe this same velocity is just like whee, like going in a circle like this, you could draw the free body diagram at the top instead and calculate the normal force and actually see what you get. You should get something less than just FG. Give it a try for practice. Okay, I'm going to do another example, not of circular motion this time, but of this lovely blank slide problem. Isn't it nice? Okay, I want to give you an example of a multiple connected object problem. And we're going to get the problem set up just to help remind you of the basic principles of how this works. Let me tell you a couple of points about this. First of all, you need to remember to be careful defining your system. And by that, I mean, well, if I've got multiple objects, do I want to consider them all as one big thing and combine them, or do I want to consider each one separately? So we'll say one combined object or separate. One combined object would mean one free body diagram. Separate would mean each one gets its own free body diagram. If you are unsure what to do, lean toward the separate. Separate will always allow you to find every possible thing in the problem. Combining them, remember, makes some of the forces potentially be inside the problem. Be an internal force, which means I can't solve for it. So the combined object can sometimes be a shortcut to an answer, but it also requires a little intuition about whether it's going to work for that particular problem. So when in doubt, go separate. Let's see, some things that we should add to this. The other thing you need to be careful about is make sure that your objects have a consistent positive acceleration direction. You need to make sure that both of them have the same direction as positive. And I'm going to make 2 additional points once I draw what the problem is going to be. I'm going to just have a pulley and a rope attached around that pulley connected to a couple of different masses. So M2 and M1. And we're going to say that it is given that M1 is accelerating down. So you're told in the problem that M1 is accelerating down. So which way is M2 accelerating? And it should be up. That's just one big rope, right? So the things that these have in common is that we'll say both objects have the same acceleration. They're moving together as one unit because it's just one rope that's connecting. They're forced to move together. And also, we can say that the tension force is the same everywhere in the rope. Both of them are being pulled on by the same rope and therefore the same tension force. So let's draw a couple of free body diagrams, one for mass 1 and one for mass 2. So since mass 1 is moving downward, I'm going to let that be the positive direction for mass 1. So this way it will be positive y, which seems a little weird, but remember we like to make the direction of motion be a positive direction. And you might remember from other problems we did with this, something like a pulley when I have different objects, it sort of just redirects the coordinate system. So in other words, if down is the positive direction, down for this one corresponds to up for the other one. Okay? So we're going to say that for mass 2, up is the positive y direction. That way, both of them are moving in the positive direction. One's not moving positive and one's moving negative. Both of their motions can be described as positive. That gives me a consistent acceleration direction, which was point 2. Yes?
So like, are you defining those axes like along the road?
It's basically along the rope, yeah.
Because like,
Straight down and straight up.
because for mass 1, like pretty much do you have the axes like turned, like the object turned upside down, basically?
Okay, so for mass 1, there is no rope in that particular direction. So I still have mass 1 oriented the way it is, but
Oh,
let
this
me
is like if mass 2 has the positive.
continue to draw. The tension force is actually there.
I see.
Okay? And the tension force is here. The rope is pulling on both of them. This one has a gravitational force that's m1g. This one has a gravitational force that's m2g. And those are all the forces that are there. Okay? The key is making sure positive is the same for both of them. One's moving up, one's moving down. We're going to call both of those positive. Once we have that, we can write out equations for both of these. So let's say for this one, the sum of forces in the y direction equals the second mass times the acceleration in the y direction. And there's only one positive force and one negative force that we'll plug in. Your question?
You just go straight to energy instead of dividing it by one.
I did this time, just to get us a little quicker to the answer. And also to save having to write FG1 and FG2, which just gets a little messy. Let's see, this one is FT minus M2G equals M2AY. So that's the equation for the second mass. And the other one looks really similar, except the signs are flipped around and it's mass 1 instead. So this time it's M1G minus FT equals M1AY. Okay. Both of those just coming from the sum of forces in the y direction for each of them. So I should probably put here, this is sum of forces y equals M1AY. Let that step out. My fault. And then a couple of things will be unknown. You'll be given a bunch of stuff. A couple of things are unknown. You've got 2 equations you can solve for them. I just wanted to show you the steps for how these problems generally work. Multiple connected objects. Ask your questions. Yes?
What about 2 objects? One is on the table, the other one is pointing down. So the first one on the table is just kind of moving sideways.
Yeah, so in the case where we had something that was like this,
Yeah.
and this one's going that and that one's going there. In that particular case, I would call that a positive direction and that a positive direction. Even though one's sideways and one's down, even though in this one was up and one's down, the directions of motion I want to call positive for both of them.
You mean positive Y, right? Or X?
Call it anything you want to. It's totally fine. So if I called this one positive X, maybe I want to call that one positive X just for consistency. But Y would be just the same. Yes, I saw another hand here. Yes.
When you explained it like this, the axis just moving up and down, that was really helpful. So can we apply that here?
You can do that here as well. Yeah, so, oops. Let's see. The difference being like, well, I don't really have two axes. So maybe if I decide that this is Y and this is X, I could take that up and around the pulley and then back down like this. In which case, that's positive and that's positive. Okay. Anyone else? I expect the most questions here with this older stuff. As we progress toward newer stuff, you're going to be like, oh, I know how to do that already. I didn't forget. Maybe. All right, that's chapter 5b and 6. Chapter 7 was kind of an intermediate chapter trying to get us to chapter 8. In chapter 7, we dealt with work. Work, you might remember, is F times displacement times the cosine of the angle between those two.
Can I ask a question?
Yeah.
Is it F of R or F of T? Is it the dimension?
T, there's no R here anywhere, I don't think.
Oh, okay, so the one that goes up on both of them is T?
Is T, yes. Tension force on both of them. What else was in chapter 7? Work. Do you remember anything else? What was that? Friction. We dealt with some friction, but we didn't learn about it there. I heard kinetic energy. That seems good. Yeah, we talked about kinetic energy. It's 1/2 mv squared. We talked about other types of energy, but we didn't really deal with them. I just introduced them here to bring them in a little later. We did the work kinetic energy theorem, which just connects those two things right above it, which is that work total is equal to the change in kinetic energy. We're going to do a problem here in a second to remind you how that works. Let's see, we did a little bit with work done by a variable force, which we said was equal to the area under the curve for a force versus position graph. And then we talked really briefly about power, but we haven't really done much with that. We've got a couple of different equations of power. Power, let's see, is work over time, and also force and velocity. That's the gist of what we covered in chapter 7. Which one? F versus PHYS. So I've got a work problem for us to do. But we can't really do it without dealing with stuff back from in chapter 5. So it serves us to get a little bit of a review as well. So there's a block that sits on a horizontal rough surface with that coefficient of friction, and it's being pulled on at an angle of 30 degrees. So the idea is that it looks like this. That's not horizontal. Is that horizontal? Not really. I'm going to keep trying until no, every one of them goes up. I can't do it right. Let's see. Yeah, that's roughly close. Why not? So let's see. There's a box that's here. Be careful. And there's a force there. Let's make that a little more tilted. 30 degrees. forces like that. It says that it is observed to move across the surface 2.3 meters. So it starts at one location and goes over here somewhere. A distance delta x equals 2.3 meters. And you'll notice most of these questions are how much work did this force do? How much work did that force do? Et cetera, et cetera, et cetera. So just for completeness, I'd like to put in the rest of the forces. They told us about this one force that's pulling on it. Name some others that are acting on the box. Gravity is pulling on it downward. What else? Normal force. And what else? There is friction. It's back that way. And that is all of the forces that we have acting on this box. So you see 5 parts to the problem. 4 of them are how much work is each of those forces doing. So it goes through all 4 forces and finds out how much work they're doing. Part B is the only one that's a little different, where it asks for the apparent weight. The apparent weight, again, is the normal force. So let's see, what is the work done by force F? So let's just start here. The work done by force F is the force times the displacement times the cosine of the angle between them. We have all of that. That's relatively easy enough, I think. So the force, they said, was 10, the displacement is 2.3, and the angle between them is 30 degrees. So let's see if I have a number for this one. Slide down. How about 19.9? And what would the units of the work be? That is in joules. Good. Okay. For part B, finding the value of the apparent weight of the box, I'm going to have to use some sum of forces stuff. So let's see. Let me go up here and say that the sum of the forces in the y direction equals MAY. It's only moving sideways, not up or down, so that acceleration is going to be 0. And then I've got 3 forces to deal with. The normal force is positive. We've got a component of the force that's there, which is F sine 30. I'll go back and draw that in for you. That's this force. And of course, there is a component this way as well, but it turns out this problem is not going to use it, I don't think. And then let's see, there's the gravitational force down, and all that has to add to give me 0. 2 forces up, 1 force down adds to 0. Okay? Yes, every part of that particular problem is from chapter 5, stuff you did on the previous exam, but you can't get through this problem without it. So the normal force is going to be equal to negative F sine theta, or sine 30, we'll go ahead and write that out, plus the gravitational force, and we can plug all of those in. So 10 sine 30 plus 5 times 9.8. I've got 44 newtons. That part at least should look really familiar from everything we've been doing for weeks and weeks. Part C, what's the answer? Go. That was good. Wow, that didn't take that long. That was just long enough to read it. Part C, the work done by the normal force. It's moving sideways, but the normal force is vertical. If there's 90 degrees between them, that force isn't doing any work, but we can write that out in a little bit more completeness and say that the work done by the normal force is the normal force times the displacement times the cosine of the angle between them, and that angle is 90 degrees. The cosine of 90 is 0, which means the work done by the normal force is 0. Okay, so you can do it mathematically or recognize they are perpendicular to each other, so that force is not doing any work. Yes?
When you say 90 degrees, that's relative to the motion of the box.
That's, that's the angle between the force you're talking about and the displacement. Okay, so there's 90 degrees between those two. Let me jump down to part E. What's the answer to part E? 0. Yeah, the gravitational force is also perpendicular to the direction it's moving. So the work done by the gravitational force is 0 for the exact same reasons. Let's put over here cosine of 90 equals 0. And then we can go back and do part D, which is a little bit more work. Parts C and E are essentially asking the same question. So A, B, C, E, D, clearly we're doing things in the proper order. You gotta love that. And D says, what's the work done by friction? So we'll use the exact same equation. The work done by the friction force is going to be the friction force times delta x times the cosine of the angle between those two things. And we know that the friction force is the coefficient of friction times the normal force. And then we'll bring down delta x and cosine theta. What's the angle this time? It is 180. Delta x is to the right, friction force is to the left. That's 180 degrees apart. So let's plug all of this in. Let's see, the coefficient of friction was 0.12. The normal force is 44. Delta x is 2.3, and it's the cosine of 180, which is going to give us a -1 out of all of this. Let's see, that should be negative 12.1 joules.
Will you ever use it?
Will you ever use 0? Yeah, if the force had been pulling straight to the right instead of at that angle, then you would use an angle of 0, which gives me 1 when I put it into the cosine. Yeah.
Can we go over like what negative work means?
Yeah, let me answer your question by asking all of your question. Take a look at what we just solved for. Notice part A, I got a positive work. Part C, I got 0. Part E, I got 0. And for part D, I got negative. Is the total work here positive or negative? It's positive. What does that mean about the object itself? Is it going to be speeding up or slowing down? Positive work means it's speeding up. I'm putting energy in. If we'd gotten negative, if that friction work was more than the work being done by the pulling, well, negative work tells me that energy is being taken out, which indicates it's slowing down. And I feel like we worked together on this question because that leads me right into what else that I wanted to do here, which is not part of the problem. But let me zoom in way down here a little bit and say that we can look at the work energy theorem or the work kinetic energy theorem, which describes what I just said. Positive work speeds it up, negative work slows it down. And we can see that this is true by solving for this. So this is kinetic energy final minus kinetic energy initial. And let's say we assume that it starts at rest. It didn't say that in the original problem, but just so we can solve for something. If it starts at rest, let's see how much this work sped the object up. Let's see how fast it's going at the end. So work total is literally add up all of those numbers. So I had a 19.9 and a 0 and another 0 and a negative 12.1. So that's work total. Add them all up. And then if this starts at rest, the initial kinetic energy is 0, and I have 1/2 mv final squared. I can find out what that final velocity is, how fast it's moving because of the work. So let's see, 19.9, and someone will have to give me this answer because I don't have it, times 2 and divide by the mass and take a square root will give us the final velocity. Some of you look like you're calculating in your head, but I don't think that's true. As you stare at the screen, you're like,
3.95.
3.95? Did you take the square root?
Yes.
Yes, 3.95?
Oh wait, sorry.
No?
Not right.
6, 4, 1, 3.94, 1.8, 7.2. I'm just making up numbers.
What was the mass?
I don't know. Somewhere up there at the top. 5. Mass was 5.
1.77.
1.77? Could be. I don't know. I don't have the number. The mass here is 5. 1.77? I haven't heard anyone disagree with either of your answers yet. So 1.77? Okay. So if it starts from rest, those forces doing that amount of work are going to make it go 1.77 meters by the time things are done. Work kinetic energy theorem. This problem is chapter 7 in a nutshell. Okay, in the back.
Could you explain more how you got cosine of 180?
Cosine of 180. For all of these work equations, it's the angle between the two things that are in the equation. So the friction force and the displacement. The friction force is pointing to the left, and the displacement is pointing to the right. Straight line, 180 degrees between. Anyone else? Yes.
So the force of friction is that a mu right there?
There is a mu right here. Yes. Question?
If the friction force and the displacement were pointing in the same direction, the angle would be 0?
If they point in the same direction, the angle is 0. Yeah. The cosine of 0 gives me 1. Okay, let me jump to chapter 8. Chapter 8 is a continuation of chapter 7, and the list of things in chapter 8 are kind of short. Let's see. So in chapter 8, we talked about conservative and non-conservative forces. Remember that conservative forces store potential energy. Conservative forces don't waste the energy, they store the potential energy. And we actually talked about 2 different types of potential energy. The gravitational kind, which is m times g times y. And we talked about the spring kind, which is 1/2 kx squared. So 2 conservative forces, gravity and spring forces, store these 2 different types of potential energies. Non-conservative forces like to lose energy. They don't store it, they just throw it away. Bad forces. Bad forces. And then we used all of this in the conservation of energy, which is really the focal point of this chapter, and in a lot of ways the focal point of everything we've been talking about for a while now. Kinetic energy initial plus potential energy initial plus kinetic energy final plus potential energy final minus WNC, the work done by any non-conservative forces. And we're going to do some examples with that. That's what's in chapter 8. Okay? So conservation of energy problems. I have 3 of them I'd like to do. Do you think conservation of energy problems might be on the exam? Especially if I'm about to do 3 of them. Yeah? And it seems kind of like it might be true. Maybe the whole test will just be one big conservation of energy problem. I mean, it won't be, but it could be. I could give you a conservation of energy problem that asks you things about both 7 and 6 as well. It's possible to put all of this into a conservation of energy problem, but I'm not going to do that. So this first problem allowed me to apologize for much of what's in it. If you just start reading a little bit, it's like, why are all these words here? So let's see. If we just go sort of right here to the bottom, this is the only part that you need to read. Murfreesboro actually is a town. This particular one's in Tennessee. I grew up there. So I used to teach at the university there, and a colleague of mine wrote this problem, so alas, that's where this comes from. There is no ice hockey team there because it's in Tennessee, so that's completely made up. So there's no Murfreesboro Mudslugs, no. There is no Bubba Joe Patterson. Actually, there probably is, but I don't think he's a hockey player, so that's gone. Nobody calls anything Slug Puppies or Murphtown. So just forget all of that. I don't know what's happening there. So you could just ignore it. Someone's playing hockey and hits a puck across the ice with that initial velocity. It slides 77 meters before stopping. End of story. So we've got some ice. Yay, ice. There's a puck. It's moving this way with an initial velocity. And over here somewhere it stops. V final equals 0. And in between the two is 77 meters. It slides 77 meters because ice doesn't have a lot of friction, but it has enough, and we'll find what the coefficient of friction is, which should be a relatively low number. So we're going to use conservation of energy here between those 2 points. And that last term, instead of non-conservative, I'm going to go ahead and write that as friction because it is the thing that's doing work. But a lot of these terms are 0. Remember, with kinetic energy, it has a velocity hiding inside. So if it's not moving, there's no kinetic energy. So it's not moving at the end. So there's no kinetic energy there. Also, with potential energy, it's about, first of all, whether there's a spring. Well, there's no springs here. I don't have to think about that. So it must be about gravity, so am I above or below the ground? The thing stays on the ground the entire time, which means it never has any gravitational potential energy. The potential energy due to gravity is 0 if it's at y equals 0. Which means all of that kinetic energy at the beginning gets taken away by friction doing work on it. That's what the equation says at this point. So 1/2 mv initial squared equals minus the work done by friction. And then we're going to plug in our equation for work, which goes back to chapter 7 and all the stuff that's there. And the only unknown that we're going to have is the coefficient of friction, which, yay, we can do a little algebra and solve for. So 1/2 mass velocity initial squared equals minus the work done by friction, which is the friction force, times the displacement times the cosine of the angle between them. What's the angle this time? Which way is the displacement? To the right. Which way is the friction? To the left. So once again, that's going to be 180 degrees. Okay? The direction it's moving or displacing and the direction friction is pointing is 180 degrees. So let's go up here and rewrite this again. 1/2 mv initial squared equals minus the friction force, which is mu times the normal force times delta x times the cosine of 180. That thing is going to give me -1. What's the normal force here? Good. I'm glad you didn't answer, because you shouldn't answer right away that quick. The way I find the normal force is by, I'm sorry, drawing a free body diagram. Which looks like that. Normal up, gravity down, friction left. And then writing the sum of forces in the y direction, which is very quickly going to tell me that the normal force is equal to the gravitational force in this problem. Okay? You might be able to recognize that at this point by looking at it. The key is Fn is not equal to mg as like a standard equation. It sometimes equals mg like it does in this particular problem. We're going to do another problem here in 2 slides where it won't be equal to mg. We'll follow the exact same approach. So now we've got 1/2 mv initial squared equals, two negatives there make a positive, so just positive mu mg delta x. The m's cancel, and you can solve for mu and get 0.11, if I remember from this morning correctly. Somewhere. No, it's 0.13, I'm sorry. There we go. A little algebra there at the end for you to do yourself to get to that answer. Does every part along the way make sense? Conservation of energy, a free body diagram hiding in the middle to find the normal force, solve for mu. And if I'm going to go home at the holidays, I need to get some plane tickets to Murphtown. I don't think they sell those because no one's ever called it Murphtown. Let's see. Next problem. A baseball is thrown vertically upwards at that velocity from a height of 1.5 meters above the ground. It goes up, reaches a maximum height, and then comes back down. What is the height above the ground that the ball reaches? So if we were to say that this is ground level, y equals 0, and maybe say that the ball starts here, which is 1.5 meters above the ground, and we throw it that direction with initial velocity, we could say that it goes up somewhere and eventually stops. Okay? So V final equals 0. Notice the starting point and the ending point are above the ground. There's potential energy everywhere. The only thing that I have is that at the top it stops, so there's no kinetic energy, and we're ignoring air resistance, and there's no friction or anything, so I can ignore that term as well. So I could say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final minus WNC, and we can let those two be 0. It stops at the end, and because there's no friction. And I'm sorry I'm having to accelerate just a little bit. Accelerate. Physics teachers that accelerate. It seems like that should happen all the time. But don't forget, I'll post the slides, and we're recording. So you have access to all of this if you don't quite catch something. So let's see. 1/2 mv squared is my kinetic energy. M times G times Y initial is that starting potential energy. And all of that is going to combine into the final potential energy, which you can solve for and get that final Y final. So the masses cancel out. Yay. And then you're a little bit of an algebra away from Y final to answer part A. Y final is 2.3 meters, which means my diagram over there is terribly not to scale, but hopefully it's enough to be instructive. So it starts at 1.5 and goes up to 2.3. It's a very sad ball toss, I think. It's like, it didn't go very far, okay?
Okay, what's the initial of the W?
What is the initial, I'm sorry?
The W?
The WNC. WNC, and we're going to set that to 0.
Why do we set that to 0?
No friction. There's nothing doing work here that's taking away energy. Okay? Part B. What is the speed of the ball when it is 2 meters above the ground? 2 meters above the ground. Well, that's somewhere in this region where it's still on its way up. So if we were to say that maybe this is 2 meters, which clearly it's not, but you get the idea. We want to find the velocity at that point. So part B is find the velocity here. We can do the exact same thing. It's just we've moved the final position. Instead of it being all the way at the top, we're going to see what's happening sort of partially up. So we can say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final minus WNC. But now it's only the lack of friction that allows me to set that to 0. Everything else stays around. We've got kinetic energy everywhere. We've got potential energy everywhere. So we have to write 1/2 mv initial squared plus mgy initial equals 1/2 mv final squared plus mgy final. And you're solving for that. Okay, there's both types of energy at both locations. Yeah.
Did you say W and C stand for?
Work done by non-conservative forces.
No.
So you should double check that you can do that algebra, but if you do it, you should get 2.5 meters per second. So it drops from being 4 meters per second to now part of the way up, it's moving 2.5. It's approaching 0 when it gets to the top, but it hasn't slowed down all the way yet. Part C here is asking about work once again. What is the work done by gravity from when the ball left the person's hand until it reaches the highest point? So from here, looking at a displacement all the way up to there, that's delta y. And the work done by gravity is going to be the force of gravity times delta y times the cosine of the angle between those two. Which way does gravity point? Down. Which way does delta y point? Up. What's the angle between up and down? And it sounds like 180 once again. So let's see, this is m times g times delta y. I get a -1 from the 180. Plugging the numbers in, we've got 0.25 kilograms times 9.8. And delta y is going from 1.5 up to 2.3, so that's 0.8. And we've got a negative sign that's going with all of that. So the work done by gravity should be about -2 joules. We have a blue problem, a red problem, and a green problem. That was fun. Any questions floating around out here? Yes, sir.
For A and B, why is work 0?
No friction. No friction.
So for the C, the only friction we have is
I'm sorry?
so for the RC or the delta y, the only thing we have is the only work is for gravitational.
Yes, it's specifically asking about the work that's done by and ignoring all of the parts of the problem. Only looking for the work done by gravity, which is the only force acting. Okay. One more review problem. One more conservation of energy, and then I'm going to make a quick list of things for Chapter 9, which we just did Chapter 9 stuff. We didn't even go very far into it, but I'll give you a list for that anyway. This problem should look a lot similar to that hockey puck problem a minute ago, except now things are on an incline. The block is kicked up an incline, and then it's going to slide a distance and stop. Same idea, okay? So the block starts there with a velocity that goes that direction, and it's going to stop up here where the final velocity will be 0, and it is 0.87 meters in between those two. This angle is 25 degrees. So once again, conservation of energy. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final minus the work that's being done by friction. And if it starts at the ground level, it has no potential energy there. And if it stops up at the top, it has no kinetic energy there. Which leaves us with these three terms. The starting kinetic energy, some of it goes into potential energy, some of it gets lost by friction. those two things take away all my kinetic energy. So 1/2 mg initial squared equals mg y final minus the work done by friction, which is force friction times some distance times the cosine of the angle between them. I'm going to call that phi this time, because we have two angles in this problem. So looking back over at the problem itself, the displacement d goes from here to here, but the friction force points exactly opposite. It's another case of 180, right? The friction is doing work to take away energy from the object. So yes, that one is going to be 180. The final height is something we don't have. So it ends up so far off the ground. This is y final, and it's not a value that's given. I'm given the hypotenuse and the angle. So we could say that the sine of 25 is y final over 0.87, which gives me y final of 0.37 meters. So we'll be able to use that here. And then inside the friction force, we have the normal force, which last time came out to be m times g. But the only way to know for sure what it is to look at the forces on the problem, which takes me through a really quick free body diagram, which looks something like that. From which you can see that the normal force minus Fg cosine theta equals 0, so the normal force here is Fg cosine theta. Or if you prefer, m times g cosine theta. The normal force is a reactive force. You have to look at the other forces to see what they add up to. And then you can rewrite out the equation and do a little bit of algebra. 1/2 mv initial squared equals mg y final plus mu times mg cosine theta times d. So taking what we just learned from all three of those things, the 180 gives me another negative sign. The friction force, we'll use the normal force and the coefficient of friction. And we found y final, which we'll end up plugging in for this number. Okay? The masses will cancel out. Yay. And let's see, what are we solving for here? The coefficient of friction comes out to be 0.11. Again, I'll let you do the algebra and plug in the numbers. That is not the primary point of the problem. Okay. Pause for questions before we do the last slide, and then we're going to finish just in time. Yay. And then the next time you see me, I'll have a big stack of papers to give you. Hopefully, I have to do that. I need to write this thing. So let's see. Chapter 9. Remember that for this chapter, concepts only. And that means only in the multiple choice. So if you think everything through, imagine 2 or 3 multiple choice problems from this slide, and that's all for chapter 9. Okay, the rest of it will come on the final exam. So what did we learn about in chapter 9? We learned about momentum. P is equal to m times v. We talked a little bit about Newton's second law and the better form of Newton's second law, which is the sum of forces is equal to the change of momentum over the time. We talked a little bit about impulse. the impulse I is equal to the change in momentum, let's see. We said that for all collisions, momentum is conserved, which means the sum of the initial momentum equals the sum of the final momentum. Again, I'm not going to ask you to solve any problems related to this. You just need to understand the ideas so you can answer 2 to 3 multiple choice on these topics. And the last thing is be able to identify collision type. We had elastic, we had inelastic, and then we had totally inelastic. I'm not going to ask you to analyze any of those more complicated equations related to that right now. Instead, just like, oh, did the object get modified or deformed or damaged in some way or not? Did it stick to the other object or not? Just the basic ideas of whether a certain thing happened and what type of collision that indicates. And that is the stuff for the exam. Your question? Delta P, yes. Study hard, send me your questions. All will be okay. Yes. You get to bring 1 page, front side only. And I will give you mine as well. Yes. Just one side. In the back? Push back the homework to tomorrow night? I probably can. Send me an email to remind me to do that. I can give you another day.
Well, you have office hours today, right?
Office hours today, yes. What's that? 2 to 3? 2 to 3. Thornton 327.